In the next subsection, I want to look at how to sort integers. And this topic is particularly important because we just talked about a lower bound for sorting for comparison-based methods, which said we cannot possibly do better than n log n in the worst case. And now I'll show you how you can beat this lower bound nevertheless. And this is another way to understand lower bounds. They tell you what you can do to crack the problem in maybe even a better time. So we've seen this lower bound of n log n comparisons, and that of course also means n log n running time because we have to execute these comparisons. But does that mean sorting always takes that time? And the answer is not necessarily, because it only applies to the comparison model. And if your algorithm is not in that model, who knows what's possible? And indeed, lower bounds can be seen as a pointer to what do you have to change in the description of the problem or the description of the algorithms to make it at least thinkable to get faster algorithms. And that's another useful thing about lower bounds. They pinpoint to the bottlenecks, in a sense, in a problem. So here, let's suppose we're not sorting arbitrary objects, but let's suppose we sort integers. So these are numbers, and we can do a lot more with integers than comparing them. We can add them up, we can compute averages, we can do all sorts of fancy arithmetic operations. Now, in particular, we can do the bit tricks that the word RAM allows. So this is something I've mentioned when we discussed the model. You can do all sorts of weird things. I'm not really going into details here, so maybe let's just leave it with that general comment. We're definitely not working in the comparison model if we start computing with these integers. So the lower bound formally doesn't apply. This doesn't say you can do it better, but it says you might be able to do better. A priori, it might seem unclear how arithmetic and arithmetic operations on integers should help for sorting. And in a sense, yes, the arithmetic operations are not what helps us, but something else helps. And so here's the algorithm that will eventually solve this. It's called counting sort, and I bet some of you have seen this before. But I want to go through it in slow-mo because it's, for one, it's a really beautiful thing to understand and appreciate this. And it's also something that we will use as a black box later in this class for something different. So if you're sorting integers, it seems natural that it's important to know how big these numbers are. And remember computers, so what I mean is the numbers are encoded in binary. So what we really ask is, what is the number of bits we need to write down the numbers that we sort? And a reasonable assumption is to say all our integers come from a range 0 up to u, and u is a power of 2, so well, up to u minus 1, and u is a power of 2, then these are exactly the b-bit positive integers, non-negative integers. That's natural, and in this setting, we can actually sort in linear time, in time theta of n plus u, and n is the number of integers. That is often linear time. And theta u space, when there's a condition attached to this here, when b is at most w. So when the number of bits we need for a single integer to write down a single integer is at most the word size. I bet many of you have seen counting sort, but maybe not with the stress of word RAM and word size. So if you've seen this before, carefully think about the limitations that it has and whether or not you were aware of these. When I first saw the whole theory of sorting, I found this very puzzling. And only when I saw the word RAM, it became clear that this makes sense and is consistent in itself. But how does counting sort work now? It's a very simple algorithm. You get the array of numbers. These are in this range. And what you do is you take a new array that has indices from 0 up to u. So essentially the entire range of your numbers. And that's the counter array. You initialize that to 0, and then you go through your input and set the counter at the position of this element. So you use the element in the array A, the numbers that we're sorting, as index in the array C. And that's a fancy way of saying determine how often each value occurs. That's just this. And once we have the counters, we can produce a sorted list of these numbers by just producing as many copies of each number as we have in the counts. That's what the second loop does. But there's no magic going on really. So the code is not too interesting. What is interesting is how does this avoid the lower bound? So should probably analyze the running time briefly to see how long it takes. So initializing the array with all zeros, that takes time linear in the length of the array. Then here we have a for loop. Each of the bodies is constant time because we're on the word ramp. We can do read and write to memory with the register content. So we load AI into a register, use that to access that memory cell. And then we execute this, well, how often? N times. So in total, it's theta n. And then the final loop, we do 2 iterations, but look at what happens. For each value in the universe, we iterate through our counts. So this has u iterations. This has number of copies, but if we sum this all up over all values for k, so this is ck, but those two together, the summation of all the ck must be n again, because we started with n numbers and these are counters. And then again, producing the output here is just constant time. So in total, this loop just takes theta n plus u time. So that's precisely our claimed running time. And let's briefly see, this is less than n log n if u is not too big. How is this possible? How does this algorithm circumvent the comparison-based lower bound? Well, the key thing is this line, where it uses the integers as array index. That's an operation that's totally fine on the word RAM, that's totally fine on our actual computers, but the comparison-based model doesn't allow this. The takeaway from this slide is this box down here. That's what we will use as a black box later in the class. If we're given n integers from a range, then we can sort it in, and the range is linear in n, then we can sort in linear time. That is not beating the lower bound in the sense that the lower bound is wrong. It means the lower bound doesn't apply to this algorithm because it only applies to comparison-based sorting methods, and this one just isn't comparison-based. All right, I wanted to point out that something very similar to this is used in the Java library for sorting byte arrays. It's not used for integers. For integers, they use a quicksort variant, and if you want to learn more about what exactly that variant does, then check out the Campus Wire post and my video on that. But if you sort a byte array, then it's essentially something like this counting sort that is used. There was a question on the analysis. Don't we calculate C of k in the outermost cycle? So let's not sure where that applies. It's probably about this loop here, I guess. We compute C of k here, but we compute it by iterating, by incrementing it one at a time. Now in this loop here, we iterate through this loop 1 or 0 times if C of k is 0. And then we don't execute this at all. So the question is, how often is this statement executed? Each execution takes constant time. And it's executed ck times for each k. And that sums up to n. So it's executed n times. The plus u comes from this first line because we have to iterate through this through all possible numbers, even if we then don't do anything with it. We still have to visit every number. I hope that answers the question. Otherwise, raise it again. Counting sort is not the end of the story for sorting integers. You can push the idea a little further, and that's called radix sort. That is essentially doing counting sort, but not on the full universe, but only part of it, and then recursing. But I don't want to spend more time on this, and we don't need this for this class. But it's worth knowing that even if the range is polynomial in n to a fixed power, you can essentially apply the same idea by iterating a constant number of times, and you still get linear time sorting then. That's still a very, very restricted world, that the integers are fairly small, bounded in terms of the length of the array, or at least polynomial in the length of the array. From the theory side, and I'm just saying this up front, so this is not in the exam. This is just for your curiosity. This is cutting-edge research on sorting. I want to briefly mention this because we're a master's class and not just undergrad's algorithms. You should be able to look a little bit beyond what's in textbooks. If we fix the size of our numbers to the word size, so we use w-bit integers and sort those, and we allow that w is an arbitrary function of n. So remember, in unit 1, we essentially fixed w as theta log n. Now, in general, this is not necessarily the case. You can have any other function for w as a function of n. And in theory, people have looked at this. And it turns out there's different ranges. If w is indeed not too big, like our assumption, then we can sort in linear time. We can sort n integers in linear time in this model using what I've just shown. On the opposite side, if w is very big, not just logarithmic, but at least more than logarithm of n squared, it's a technical reason why this is necessary. So this means there is a positive epsilon, some constant greater than 0. So that w is omega of log 2 plus epsilon n. Then you can again sort in linear time, but with a different sorting algorithm. And for the range in between, it's an open problem. We don't know. There is a very complicated algorithm with this obscure running time n times square root of log of n that uses hashing and randomization and a lot of advanced techniques. But we have no idea if this is best possible. I think up to now, we don't know if linear time is the right answer, like in the other cases, or if there is indeed a weird range for w in between where this is not possible asymptotically. For the rest of this unit, though, you can forget about this part. What you need to take from this subsection is really this box down here. And the general gist from this, that there is a little bit more to sorting than the comparison-based model. But both for practical applications and for the rest of the theoretical topics, we will restrict ourselves to the comparison model in this unit. To wrap up, I have a last question to see if you're mastering these kinds of considerations. So this is a mean question because I ask you to select all the answers that are correct, not just a single one. And the statement is, my computer, I mean, this is literally true for this laptop and most of our other computers, it has 60-bit words, so W is 64. So if I use an int, say in Java or in C, it has 64 bits. It's an integer of 64 bits and say unsigned. So does that mean I can sort an int array of length n in this time? Let's see what you have to say about this. I'm very curious and want to give you a minute to do this. I think after this subsection, it's a good time also to do our little break. Okay, let me switch to the poll, but I don't want to show the answers just yet. Honestly, at least 30 people answering. One more. We're stuck at 29. Okay, something moved, but someone was just modifying their results. Aha, okay. Good. Let me show the results now. And so we have a lot of people saying that we can sort in n log n time. And that's the easiest one. That is definitely correct because we can use a method like merge sort, and then we can sort an arbitrary collection of n objects in n log n time. It doesn't even matter that these are integers or ints, 64-bit integers in our sense. So this is definitely true. The more interesting ones are clearly the first two. Constant time is probably clear that this is too ambitious. If the length of the array is unrestricted, I cannot even read the input in that time. So this is not true. But maybe also the last answer is true. And let me show you what I marked as correct. And I want to discuss this briefly. I marked 3 answers correct, and this is partly inconsistent, and I want to explain why. We talked about the answer C. That's definitely correct, and you could just use merge sort. So that one's easy. The order n time, that's a tricky one. What we can do is theta n plus u. This is counting sort. Now, if u is actually 2 to the 64, that is the same as theta n because it's plus a constant, and a constant is never bigger than n. So in terms of theta classes, we can do it in order n time. And that, of course, also implies we can do it in n log n time. Now, it's not true that we can do it in time proportional to n unless we allow this constant of proportionality to be arbitrarily big, or to depend on the 64-bit. In a sense, this is okay. I mean, depends on how you really, depends on what you define proportional to mean. Maybe I shouldn't have marked it as wrong, because it's arguably similar to O of n. But the point is that we need this plus u in either way, and whatever you say, it has to allow this plus u. That's the key point. And the last point also has some truth in it, because we can only do the faster sort than the merge sort if we have extra space, and not just length n extra space, but we need theta u space for counting sort. And even if we go to radix sort, it's not clear if we can make the space just depend on n. Suppose n is very, very small. Maybe n is just 10, but the numbers are really big, and you just have these 10 cells. It's not clear if you can sort this in time that only depends on n. So all of the answers here have some merit to it. Again, instead of arguing which of the answers are precisely true or not, what you should keep in mind is the red box. You can do counting sort, you can sort in linear time, but linear in n and the universe size. With slight tricks possible with radix sort, etc. But you usually don't get easily away from the plus u entirely. With that word of caution, I want to close this section on integer sorting.